Assalamualaikum and greetings to Prof. Andrew and Dr. Daniel. My name is Muhammad Irfan bin Ahmad Shayuri, matrix number 63405. Today, I will be presenting my final year project entitled Improvement of Drying Effectiveness for Palm Oil Sludge Drying Machine. The project was supervised by I.R. Rudianto and Prof. Abdullah Yassin. This is the outline for the presentation. Rather than using chemical fertilizer, palm oil meal sludge can be utilized as cheap organic fertilizer. However, the palm oil meal sludge needs to be dried beforehand. Some of palm oil companies are still using conventional method to dry the POMS. Conventional methods are less effective and some of it are phasing out due to high energy consumption. The drying machine is equipped with the combination of centrifugation and heating system. The centrifugation method is a very suitable method to reduce the water content since the sludge is initially in the form of semi-solid and contain a lot amount of water. As for the heating system, forced air convection is designed to increase the drying rate of the sludge. Previous design contained problems such as difficulty in increasing and maintaining temperature. The first objective is to design drying machine for palm oil meal sludge, and the second objective is to improve the previous machine design in terms of moisture content removal and the drying rate. From the literature study, M. Nizar 2016 says that the most suitable moisture content for composting is 55%. U 2020 state that high and low rotational speed resulted higher evenness of drying. Based on Diaz 2017, circular baffle plate with greatest radius is the best design compared to others. And lastly, Khatir 2012 state that airflow in oven chamber is turbulent. This can be confirmed by the calculation of Reynolds number. This table shows the advantage and problems from the previous design. As highlighted, both designs have the same common problems, which are difficulty in increasing and maintaining temperature. However, it is also stated in previous report that the previous machine have some vibration and stability issue. Some issues have arises due to the previous design problem. The issues are uneven drying of the sludge, inconsistent product output, and stickiness issue at the rotary drum. This is the methodology for the project. As we can see, three methods had been used for the redesign process of the drying machine. Reynolds average Navier-Stokes runs was chosen to be the CFD model for this project. This is because Run's method is suitable for large complex systems. Run's is also cost efficient and less time consuming compared to large eddy simulation LES and renormalization group RNG. Under Run's method, there are several models that need to be chosen from. In this project, standard K epsilon was chosen because it has good convergence. It is robust and economical, and finally, it is suitable for external flow complex geometry. Meshing is a key component of the engineering simulation process, in which complex geometries are broken down into simple parts that can be utilized as discrete local simplification of the larger domain. The mesh quality has a significant impact on the quality of the CFD result. The basic guideline of tetrahedral mesh skewness for most flows should be kept below 0.95 with an average values of less than 0.33. This is according from the ANSYS Fluent Documentation 2009. Based on figure 1, the maximum skewness is 0.92549 and the average value is 0.23039. The element size was determined by a grid independent study. There are 4 design parameters that need to be considered for redesigning process. The parameters are support system, heating chamber, roller support, and centrifugation system. Support system is used to have a better stability. Heating chamber is to reduce the time taken to preheat and maintain the temperature during the drying process. Also, it will provide a uniform drying for the sludge. Roller support will reduce vibration during the drying process. And lastly, centrifugation system will spin suspended solid by means of centrifugation. So, this is the finalized design for the improved palm oil sludge drying machine. The table shows the design configuration of all designs which are from 2018 and 2019 and the new design. As we can see, there are 3 major improvements from the previous design. The first one is the drum size. New design have bigger drum size to increase the load of sludge. Next, new design have better air circulation compared to previous design due to better ventilation system. This had been achieved by increasing the number of exhaust fan for inlet and outlet. Lastly, the stability of the drying machine was increased due to the increment of the number of support roller to support the drum during the drying process. As we can see, 2018 design has no support roller and 2019 design has only 2 support roller. The new design have total of 4 roller to support the drum dryer. Next is the CFD model for the heating chamber. As we can see on the left side, there are basically 2 design configurations for the simulation. The first configuration have 2 inlets on the side and 2 outlets at the top. For the second configuration, the inlets are at the top and the outlets are at the side. Pictures on the right side shows the plane that are used to extract the values of temperature and air distribution. Plane 1 and plane 2 are located at the location of the sludge to get the most precise reading of temperature and air velocity throughout the drying process. These are the simulation video for design configuration 1. On the left side is the simulation of heat distribution inside the heating chamber, and on the right side is the video of velocity streamline for design configuration 1. As we can see, the inlet for design configuration 1 is located at the side and the outlet is located at the top. Next are the simulation video for design configuration 2. On the left side is the simulation of heat distribution inside the heating chamber, and on the right side is the video of velocity streamline for design configuration 2. As we can see, the inlet for design configuration 2 is located at the top and the outlet is located at the side of the heating chamber. In order to obtain the best possible configuration, the simulation was divided into 5 cases. Each cases have 2 design configurations that had been shown before. The difference for each cases are the air inlet velocity. Result from the simulation was extracted and graph of temperature against time are plotted. The graph shows the time taken for each design configuration to achieve the desired temperature, which is 313 Kelvin. As we can see from the graph, case 4 and 5 have the steepest graph and case 1 and 2 has the less steep graph. Also from the graph, we can obtain the best design configuration for each cases. As we can see, design configuration 1 are slightly better in terms of time taken to heat up the heating chamber compared to design configuration 2. From the results, we can see that case 1 have the longest time taken to heat up the heating chamber, followed by case 2, case 3, case 4, and case 5 having the shortest time to heat up the heating chamber. This slide shows the velocity streamline for all cases and design configuration. As we can see, design configuration 1 have better velocity streamline compared to design configuration 2. This is because the velocity streamline for design configuration 1 cover almost all part of the heating chamber, especially along the rotary drum, which consists of wet sludge. This can help the sludge to evaporate more water during the process due to more hot air are in contact with the sludge. The velocity streamline for design configuration 2 is not the best because the velocity streamline are only focused on the middle part of the heating chamber. This can cause the sludge to be dry unevenly and can cause inconsistent product output. As from previous result, we can conclude that design configuration 1 are better in terms of time to heat up the heating chamber compared to design configuration 2. This is because, as we can see from the graph, design configuration 1 always have shorter time taken to heat up the heating chamber compared to design configuration 2, almost on all cases. Moreover, from previous slide, design configuration 1 have better velocity streamline which promote better airflow. Case 1, which has the slowest air velocity inlet, takes the longest time to heat up the heating chamber, and case 5 has the shortest time to heat up the heating chamber. Although case 5 has the shortest time, it is not the best because high air velocity will cause the airflow inside the heating chamber to be too fast and will prevent the sludge from heating up and evaporate during drying process. Hence, it will reduce the drying rate of the sludge. From the graph, case 3 have the most optimum air inlet velocity, which is 2 meters per second, because as we can see, the gradient of the red line is starting to become less steep at case 3. This shows that case 3 configuration design 1 is the most optimal design configuration for the heating chamber. In conclusion, the time taken to heat up the heating chamber is greatly reduced compared to previous design. Rate of drying for the sludge is also improved by finding the optimum air velocity for the inlet. And lastly, uneven drying of sludge and inconsistent product output can be overcome by improving the airflow and air circulation inside the chamber. For recommendation, it is recommended to do an experimental approach for current setup to get a better result. The second recommendation is to implement a new inlet with variable diffuse angle. That's all from me. Thank you.